All right, so I thought what I would do in light of, well, just to give you a little more um, information with regard to analyzing designs is I'll start with well, it's quite a bit different than the project you're working on, but basically the goal is still the same. So here's a clamp assembly. This is shown here. This is actually a particular clamp made by Destaco, and for example, if you look in MSC, you can get that. You can buy this clamp. It holds 1,200 pounds. So basically, if you clamp it down, it can resist 1,200 pounds acting up without it disengaging. All right. Okay, let's close this down. So it consists of several parts, some linkages, right? Pins, typical type of design. Not a very complicated design, but still moderately complex. You have one, two, three, four, or five significant parts going on here. Okay, so I figured what I would do is kind of take you through how I would do the analysis to justify the design requirements for something like this. All right. So I'll start off and talk about the top level requirements. I think I'll probably try to do that in this video. I'll consider just two, and then we'll take those and go through a couple of the subcomponents and do some of the analysis, the hand calculations, derive design requirements, obviously, to get those to set up those hand calculations, and maybe I'll do a couple FEAs just to give you an example of the FEA. Okay, so if we look at this part here, right? The obvious condition, and I wish I could point, but I can't really point to my CAD screen. You know, I can point in this window, but not in the CAD screen. If you look at the clamp, you know, they're saying it can hold 1,200 pounds of clamping force. So that means this tip can exert 12,000 pounds down on a clamp specimen, or in other words, acting up on this point, there could be 1,200 pounds, right? So that would be one load condition. Nothing happening with the handle, but simply just 1,200 pounds acting up at this tip. On this level, you would also have the external forces of through the fasteners holding it down to the table. And then obviously internally, there would be several internal reaction forces between the pins and the various elements. Okay, so that would be one load case, right? The second load case would be that one might consider is what happens when somebody puts force actually onto the handle. So that's a separate issue. Once the clamp is over center, actually if you look really closely, the way this works is you can see these two holes don't quite go vertically. This link just swings a little bit over center, which locks the clamp down. All right. So kinematically, it's such that you can't unlock the clamp by putting force up here. Theoretically, it should take infinite force to disengage it, but obviously you have structural failures that limit that clamping force. But another situation would be how much, somebody exerting a significant amount of force on this handle, okay? And so to treat that, let's pose the design requirement in a second way. Let's determine what is the maximum force somebody can apply to that handle, okay? We probably should have calculated up front and figured out what it could be and then pose it as a design requirement. But in this particular case, let's, imagine we can flip it a little bit. And I'll say, let's find the force on here. But that also could be posed as a design requirement. Can this design survive X amount of force acting on this handle? Now, when you do that, there will be an up force acting here, as well as the forces through the bolts. Okay? Well, let me just stop the video right now. I'll call it part one, and then I'll come back part two. What I'll do next is set up the free body diagrams to define those two top level load cases, and then we'll pick a couple parts. Like I think maybe we'll pick this component and maybe the 3-point element of the arm, or maybe this component, or maybe this component, and go through and get the derived design requirements and do the analysis on there. Okay?